So till now, we have seen 2D scatter plots. We have also seen 3D scatter plots, and we realized that we can't do 4D scatter plots, but we've seen pair plots and things like that. The obvious question that must be running in your mind is, what about 1D scatter plots? We have never discussed about them. So let's see how to plot a 1D scatter plot, understand what are the problems with doing a simple 1D scatter plots, and what are how to get around them using ideas like histogram, probability density function, and cumulative density function. Okay, don't worry about the terminology. It's very, very simple ideas. We'll go over them one by one slowly. Now, let's look at a simple code snippet here. The code snippet says that I'm taking my iris data frame, and I'm taking all the points that correspond to setosa, and I'm putting them in a data frame called iris setosa. Similarly, I'm creating a data frame called iris virginica and iris versicolor. Now, what I'm doing here is I'm plotting such that my x-axis is for the setosa flowers, I'm plotting my x-axis as petal length. My y-axis, I'm just putting values, all values equal to 0. Similarly, I'm plotting versicolor and virginica petal lengths on x-axis, and I'm taking all the y values to be equal to 0. Now, when I do that, I get a plot like this. Now, of course, I know I'm missing legend and I'm missing axes here, so I'll write that down quickly. My x-axis here is petal length. My y-axis means nothing, and hence you see all the values at 0. This is your setosa, this is your virginica, and this is your versicolor, right? Your green is versicolor, your orange is virginica, your blue is setosa. Now, quickly what you'll realize is, and the way, how did we plot them? We plotted them using a function, of course, but we put 1 point for each observation that we have with this value of petal length. So this corresponds to your setosa. So this corresponds to your virginica and versicolor. Right? One problem that you immediately notice is at this place, I know that there is only 1 point. At this place, I know that there is 1 point. I know that there are 2 points here. What about regions like this? We don't know how many points exist because all the points are overlapping like crazy. Similarly, we don't know how many points exist here. They're overlapping like crazy. Similarly, we don't know how many points are here. And because I plotted the green points after my orange points, green points are overlapping the orange points, and I don't get to see the orange points that are behind here. So a 1D scatter plot like this is very, very hard to read. Now, because one of the big drawbacks is I don't know how many points are here, which is very important for me to know. To determine, okay, if there is 1 point here, or if there are 10 points, or if there are 1,000 points. Of course, we can't have 1,000 points because the total number of points here itself is 50. So I don't know if there are 20 points or if there are 10 points. I don't know any of it. So one way we can modify this plot is doing something like this. Very, very simple hack. Let's just take the setosa points here, right? This is my x-axis. My x-axis is my petal length, of course. And let's assume this is 1 and this is 2. And what I'm doing is I'm breaking. So I know that all the points lie between 1 and 2. So what I'll do here is I'll break this region into smaller buckets or smaller intervals. Let's assume I break it into 5 intervals, 1.2, 1.4, 1.6, 1.8, and 2. So I've broken it up into 5 intervals. And what I'm saying here, my y-axis, my x-axis remains the same. So I'll say how many points exist between 1 and 1.2. Let's assume there are 2 points that exist between 1 and 1.2. So I'll put my y-axis now is basically count of number of points that exist in each of these windows. Similarly, between 1.2 and 1.4, let's assume there are 4 points. Similarly, between 1.4 and 1.6, let's assume there are more points, so on and so forth. So now I'm drawing, this is a variation of my 1D scatter plot because the only variable I have is my petal length. The y-axis is not petal width or sepal length. It's basically a count of how many points exist in each of these regions, right? Such a plot. So now if I just plot it like this, if I just say, okay, that I will build a tower-like structure around it, okay. Okay. The moment I plot something like this is called a histogram. This is called a histogram, where my y-axis is basically counts, my x-axis is the variable or the feature that I'm interested in, and my y-axis basically says how many points exist in this window between 1 and 1.2. The moment you see the histogram, it makes far more sense than your 1D scatter plot. Because now I can answer the question, how many points are here in this window? How many points are there in this window? So such a thing is called a histogram. Now let's go and look at simple code to plot histograms and some variations of histograms. The code again is very, very simple here. The code basically says, okay, that we are using Seaborn. Again, using Seaborn is very, very helpful because it gives us beautiful looking plots very quickly, very fast. And all my coloring is using species. The size of the plot is 5. And I'm doing something called a distribution plot. We'll come to understand what a distribution is more detail when we learn statistics and probability. But this is called a distribution plot, and I'm plotting the distribution of petal length. And I want to add the legend. So the code is very, very straightforward, as you would have realized it. So let's go and understand this now. So of course, my blue is setosa, my orange is versicolor, green is virginica. So as soon as you see this, so this tower-like structure that I just drew a while ago is exactly what you're seeing in this light blue shade, right? So this is called a histogram. So to be very specific, this is the histogram of petal lengths of setosa flower, right? Similarly, this light orange thing is a histogram of petal lengths of versicolor flowers. Similarly, this is the histogram of petal lengths of virginica. Now, as soon as you see this, you're getting a very interesting understanding. See, this is again, my x-axis is only petal length. My y-axis basically is counts. My y-axis says how many points exist in this small window, right? So given any point here, the height of this plot of my histogram tells me how many points exist in this small window. And this is far more readable. Now I know by looking at this plot quickly, I know, oh, that lot of setosa flowers actually have a value of about, let's assume this is 1.6 here. 1.6 is what we find as the petal length for a lot of setosa flowers. Similarly, if you look at this, we see that, okay, 4.5 is what we find we often find as, because the height is more. The height here represents how often do we find this petal length in these types of flowers. That's what the height here represents. That's because it's a count, right? Because this is basically a count of number of flowers we find given a petal length, right? Now you might wonder, what are these smoothed lines? These smooth lines are called probability density functions. I'll explain this terminology. So what it says is simple. This blue line, if you want to think about it very simply, it is basically a smoothed form of your jagged lines here. So if you look at this, if I join the centers of each of these buildings, what I get is a smooth approximation, right? So your blue line also indicates, so for example, if I take this value, your blue line basically tells me roughly what is the number of points that I will encounter here. Then you might say this value and this value differ. So the dark blue line that you see, which is called the PDF, right, is a smoothed form of your histogram. Okay, we will understand PDFs in more detail when we learn statistics and probability. But for now, just remember that PDF is basically a smoothed histogram. A smoothed histogram, right? Now, how do we smooth it? There is something called kernel density estimation that we will learn slowly as we go on how to do kernel density estimation when we learn about Gaussian distribution and things like that. For now, just remember that PDF is nothing but a smoothed form of your histogram. We understand what are histograms, right? Histograms are nothing but they represent how many points exist for each value of on your x-axis. Histogram is basically a XY plot where x-axis you have the values corresponding to the variable that you're interested in, which is petal length in this case, and y-axis represents how often or how many times you find a data point corresponding to a given petal length. Okay, now given this, first thing that I know, let's look at what I can understand quickly from this. The first thing that I can quickly understand here is that we don't see any setosa flowers with a value of greater than equal to 2 by just looking at the histogram or the PDF. But I do know that there are, so let's assume I want to build a model only using petal length. Let's look at that, right? I can say if petal length is less than 2, then setosa, right? Less than equal to 2, right? Because I don't find any setosa flowers beyond a petal length of 2, right? So by using a simple 1D scatter plot equivalent called a histogram, right? By just using this histogram, I can build a model very, very quickly, very, very elegantly, right? This is how I get my setosa. Now comes the hard problem. What type of rule will I write for my versicolor and virginica. That's a hard one, because if you see, the histograms of your green and orange points is overlapping. Even your PDFs are overlapping. PDF is basically nothing but a smooth form of your histogram, right? If you see, it goes very, very close to what your histogram is, right? So if you see, the PDF of the probability density function of your versicolor and virginica are overlapping in this region, right? This is your overlap region, right? This region is your overlap region. So now the question is, if I have only petal length as my only feature, how do I write a simple if-else condition, right? I could say, so now I can say, okay, I'll take this value. So I'll say if petal length is greater than 2 and, right, and petal length is less than equal to 5.5, then versicolor, right? If I do that, what happens is all these points, so in this region between your 4.5 to 5.5, there are a bunch of virginica flowers also, which you're going to declare as versicolor, right? On the other hand, if you wrote your model like this, if petal length is greater than 2 and petal length is, so if I use this as my threshold, right? If I say, and if petal length is less than equal to 4, then versicolor, right? So these are basically thresholds that I'm setting, right? So I know that beyond 2, there is no setosa, so there has to be only versicolor or virginica. And now I'm saying anything that lies in this region is virginica. Sorry, is versicolor, I'm sorry. But that's wrong, because what happens is there are a lot of versicolor points even beyond 4, right? So I have to make a mistake. By setting thresholds here, I have to make a mistake. I can't get rid of it, right? So my final model could look like this. If petal length is less than equal to 2, then setosa, else, right? If petal length is, so where do I choose my threshold? What is the right place to choose a threshold? So one gut feel that I have here is, what if I choose this value? Let's call this value 4.7, because this is very close to 5, right? So if I say petal length less than 4.7, then versicolor, else virginica. So imagine if I write a simple if-else condition as this model. Of course, I'm going to make mistakes. For setosa, I make no mistake because all points are less than equal to 2. I'm going to make no mistakes declaring setosa flowers as setosa. But now there is a small problem. Since I've chosen the intersection of both of these probability density functions, this intersection point, as my threshold, this is my threshold that I've chosen, right? 4.7. You might ask, why did you choose 4.7? Why not 4, or why not 5, or why not some other number? Because we know that whenever we find, so let's take this example. The reason I chose 4.7 and not 5 is as follows. So suppose, imagine if I get a flower which has a value of let's assume I get a flower which has a value of 5. Okay, so I picked up a flower from the garden and I got its petal length as 5. Now, which of these two has a higher chance? Which of these two has a higher chance of it belonging to? Now, if you look at this 5 value, what is a chance? What is a probability? So the x-axis, so for probability density, you can think of this as chances, because you find more points there, right? So the moment you see 5 here, you can say that, okay, I typically find only a small number of points of versicolor type, and I find more points of virginica type whenever I see a petal length of 5. And hence, we should declare, whenever I see a value of 5, I should declare that point as virginica and not versicolor, because when in my data set of 150 points, I find more virginica points with a petal length of 5 and fewer versicolor flowers which have a petal length of 5, right? Because this orange plot is below for a given value. Since the orange plot is below the green plot, I give preference to the green plot. Now, at the intersection point here, none of them win, right? So for example, if I get a value of, let's say, 4.5 here, at 4.5, what's happening? I find more flowers of the type versicolor, right, than of the type virginica, right? Because this orange plot corresponding to 4.5 is above the green plot, right? So when I get 4.5, I will declare it as versicolor, because in my data set, I find more points. I have more proof that it probably belongs. Of course, there will be some errors. I'm not saying we are not going to make errors. We're going to make some errors. But my best gut feel is, since I've seen a lot of flowers which belong to versicolor, which have a petal length of 4.5 than virginica flowers, I will go and give my decision as versicolor and not virginica. So if you look at that argument, this intersection point will be the best place to set your threshold, right? So remember, by just looking at our density, this is also called a density plot. Why is it called a density plot? Because my height here represents how many points exist at each of these intervals, or it tells me how dense each of these regions are, right? So since more points exist here, right, this region is much more denser than this region, right? So, and hence it's called a density plot. We'll come to understand what is probability density function a while later. But for now, you can just think of it as a smooth form of histogram. Now, having learned that, and remember, PDFs and histograms are extremely useful if you want to build models with only one feature, right? And this is a much better visualization of data than your 1D scatter plot. Having said that, let's go a little down and understand a slightly related concept called cumulative density function.